So in our previous class, we looked at work energy and also went on to look at conservative forces. And finally, we also looked at the idea of the conservation of energy when a conservative force is present, and when a non-conservative force is present, we saw how the conservation of energy plays out. So we looked at the conservation of energy in terms of this form: change in PE plus change in KE is equals to 0. This is mechanical forms of energy only, and when non-conservative forces are absent. And then we also saw that change in PE plus change in KE will be equals to the work done by the non-conservative force. That is, if non-conservative forces like friction are present. So these are the two forms of the conservation of energy that we saw. One is for when we don't have non-conservative forces, and we gave examples of non-conservative forces to say a very good example is frictional forces. Those are non-conservative forces. So if friction is present, the conservation of energy that we use will be this one. But if friction is not present, then we'll use this version. But in tonight's class, what we want to look at is the last component of this unit, power. So I want to describe what power is. We want to define power and look at some questions that we can work out using the concept of power. So by definition, power is just the rate of doing work. So by rate, of course, it means we are comparing, it's a matter of how fast work is being done. So because of that, if we are going to calculate power, so I'll use capital P for power. So if we are going to calculate power, then we would have to divide the work done divided by the time taken. So this is time taken. So this is how we calculate power, or P is equals to work done over time. But we saw various definitions of what work done is. We saw that work done can be calculated using the formula force times distance. We also saw that work done can be calculated as the change in energy. Okay, so let's just silence that. So we also saw that work done can be calculated in terms of the change in energy. And to be specific, at one point, work done came out as the change in kinetic energy. And at some point, work done came out as the change in potential energy. But generally, what these two statements are, where they're coming from, it's from the fact that work done can be determined by looking at how much energy is changing, so the change in energy. But we ended up with just strictly change in KE and strictly change in PE. This is in an event where potential energy is not changing, and this is an event where kinetic energy is not changing. But generally, they're coming from just changing energy. Now, let's see what happens here. If we go back to the definition of power that we've just put, perhaps before I start playing around with that definition of power, let's look at the unit for power. If you look at the unit for power, what you have on top when it comes to power is energy, change in energy, for example, over time. Or even if I use work done over time, you have to observe that work done will have the unit of joules. Work done will have the unit of joules. It's also an energy there. And then time here, of course, you know to say this is the second. So the unit for power can be taken to be the joule per second. Or more specifically, or more strictly, the unit for power will be taken to be the watt. In other words, 1 joule per second is actually what gives you 1 watt. So this is the unit for power. But also, because work done can also be measured in Newton meter, this kind of implies that it's possible for you to give power using the Newton meter per second, where this is the unit for work done, and this is the unit for time. So this can also be related to the watt as well. So you can say 1 watt is also equals to this. Okay, now let's go back to the definition of power. We said power is equals to work done over time. But what is work done? Well, work done, we sort to say work done is just force times distance. And to be specific, work done, we defined it as the product of the force times the distance moved in the direction of the force. The fact that when I'm saying the distance moved, I am specifying the direction. That means that it's not necessarily distance. It is actually displacement I'm talking about, because it's displacement that has a direction that depends on the direction you are taking. So in other words, when I say force times d here, because the distance I'm placing here does have a specific direction, it implies that this is actually displacement here. But in terms of just using it in normal terms, we just keep on saying distance, distance, distance. But the fact that I am using it I'm using it in a specified direction, it actually means this is a displacement. And this has to be divided by time. So this numerator part, this is work done. The denominator, that is time. But what I want you to focus on is just this part here, these two. See, this expression can be written as force on its own, then multiplying the d, the displacement here, divided by the time. You know to say this is the same as that. What does this imply? Well, now it means that when you look at these two, what quantity do you think this is? What are they going to give you? Try to observe those two, and what do you think those two will give you? So what do you guys think? Those two, what will they give you? Velocity. Yes, velocity. So, yes, Messi, sometimes you can say speed, but you're saying speed because you are taking d here to mean distance. You're taking d here to mean distance, and t, of course, to mean time. That's why you're saying speed. But this is actually velocity. You know, speed and velocity are used interchangeably every now and then. So it's okay that that you take this to be speed. Sometimes it's what you have to take. But because I am specifying that d here has direction, meaning this is displacement, it now tells us that this quantity is actually velocity, meaning that power now can be written as force multiplying velocity. So this can also be taken as a formula for power, force times velocity. The only key thing here is because the distance or the displacement, I can say the distance here has to be in the same direction as the force. It implies that even these two quantities, because what gives the direction to the velocity is the distance. So now this definition, if I use force and displacement, force and velocity, it now implies that the velocity here has to be in the same direction as the force. What am I saying there? If you had an inclined plane like this one, and then you have, let's say, I can say it's a cheetah, or I can say it's a box that is sliding, or yeah, I can even say it's a box that is being pushed up by an engine. So let's say you have a box that is moving in this direction, and the velocity is 3 meters per second. And yeah, you have something that is moving at this rate, constant velocity. Okay, so we do have, okay, those were earlier comments. So it's moving up at that rate. And then what else do we need here? We need the force. So let's say it's moving under a constant force F. It's being pushed up under a constant force. I can even say the force being applied on it, I can even put it here such that it is at an angle. And I can give the angle here as theta. So the applied force here is F. So if this force gives this object this velocity, and the question is, what is the work done, the power output from this force? Now, of course, what this is now telling us is that all we need is the force. Of course, to work it out completely, you would need to also account for other forces that are present, because what you need is the resultant force actually pushing this object. So if F is just what is applied, then you don't want to multiply the F with that 3. You need the average or the net force acting on the object. So let's say this is what you have, and the direction is in that direction. What I was trying to emphasize here is for you to use this, you need the force and the velocity to be in the same direction. If the velocity is along the inclined plane, then you need the force to also be acting along that inclined plane. So you will have to, again, get a component of the force that will be acting along the inclined plane. You see that this comes out as F cos theta. So this is the force that will actually be doing something, contributing to that 3 meters per second. But in this case, you really don't want to multiply the F cos theta with the 3 and say this is what is actually giving you the power. Why is that? Because you know to say there's going to be another force present. If you do this, what this will give you will be the power output from the engine. But because there is another force present, there's going to also be another form of power present. The overall power or the useful power in the end will have to be a contribution of what those two present forces are doing. So I just wanted to put that across because I brought this up. But all I wanted to specify or to emphasize here is that you don't multiply the force like this. You need a piece of the force which will be in the same axis as the velocity. These two must be in the same direction. Not necessarily in the same direction, but just in the same axis. It's okay if one is like this and the other one is like this. You know to say one of them will have to be negative, but here they are in the same axis, so you can multiply them, but just one has to be negative. So this was just something general when it comes to the use of that formula for power. What we now want to see are different examples that we can work out using the concepts that we have just described. Consider an example or a case like this one. So let's have this as an example. So in this example, what are they saying? We have a pump that is needed to lift water from a well through a height of 3.0 meters. So the height we have to lift this water is 3.0 meters. What else are they saying? At a rate, look at this. They are giving us a rate. They're not really saying anything, but that's just a rate now. 0.6 kgs per minute. So that's the rate that they're giving us. Now the question is, what is the minimum power of the pump in watts? So what is the minimum power? So we want to find the power here. And they're saying in the first part, they want us to give the answer in watts. And in the second part, they want us to give the answer in horsepower. So in this case, you can just Google the relationship between the watt and the horsepower. When you use these formulas, we know to say the answer we'll get would directly be in horsepower, in watts. So if you wanted to convert those from watts to horsepower, you can just check out the conversion, how the two relate. But let's try to first calculate this and see what we will find. Okay, so let us begin. We're looking for power. So we start with the basics. What is power and how do we calculate power? So by definition, power is work done over time. But what is happening in this case? They're saying that this is a pump and it is needed to lift water from a well through a height of 3 meters. Okay, so we're lifting water. And if we're going to lift water, we know to say we are lifting the water vertically upwards. So what are they saying? The water is being lifted at this rate, 0.6 kgs per minute. Sir, can you read the question again? Okay, so the question reads, a pump is needed to lift water from a well through a height of 3 meters at a rate of 0.6 kgs per minute. So that's that first part. A pump is needed to lift water from a well through a height of 3 meters at a rate of 0.6 kgs per minute. What must be the minimum power of the pump in watts? Okay, so we need to understand what is happening. So it's like we have water that is being lifted. And let's say this is the initial level where the water is coming from. And the water has to be lifted from this level to somewhere higher. Let's say to somewhere here, vertically upwards. Yeah, somewhere here. So that is where the water is being lifted to. So let's take this to be the initial position. Height is equals to 0. It implies that this is the final position. Height, final, is equals to that 3 meters. They're saying we're lifting it up to 3 meters. Now, the next thing here is to calculate power, you've seen we need the work done. So that's the first thing we want to see. We need the work done. So how do we calculate the work done when the water is being lifted from here to that position? How would you calculate the work done in this case? And I want to try this. What method did you use? Just say the method, don't have to do it all the way.
How about using the work done is equals to the change in potential energy?
Exactly. Because this is a motor, the assumption here is that it's lifting the water up without changing the velocity. So it's at a constant speed. In fact, this can be seen to be implied by this statement here. At a rate, this rate is constant, it's not changing. So we expect that this is being lifted without changing the kinetic energy. So because of that, the work done here can be calculated by getting the change in potential energy. Excuse. But how do you get the change in potential energy? It's PE final minus PE initial. And how do you get these quantities? PE final, it's mg H final minus mg H initial. But what is mg H? What is the H initial? We saw H initial is 0. That is our reference point. I haven't understood the question. Okay, so here's what is happening. You have water that is somewhere at this level, and then this motor is lifting the water to some new position. In the first part, my question is, how do you calculate the work done if you have to lift the water from the ground or from some reference point where the height is 0 to some new position where the height is 3 meters? This is what we have. Now, the first part I'm saying, how do you calculate the work you do in lifting this? The overall question is asking us for the power output, the minimum power needed to lift the water. Now, to lift the water, we saw that power is equals to work done over time. So because this is work done over time, that is why I first want to concentrate on how I would find the work done. After that, I'll come and sort out the problem for time. So if I wanted to find the work done, I'll be like, okay, so I am just lifting the water from some reference height at the ground here, where the only energy it has is the potential energy. It does have kinetic energy, but here kinetic energy is not changing. So we're only focusing on PE. So here it is mg H initial. But if I take H initial to be 0, my reference point, it means that height will be 0, making the whole term here to be 0. At the topmost point here, now we have PE final. PE final will be mg H final. And here H final has a value. And when you look at the value for H final, it's 3 meters. This is 3 meters above. So I can substitute 3. Sorry, I wrote 3 meters per second. This is just 3 meters. Yeah. So I can put 3 where there's H final, and this becomes 3 mg. I know the value for g, so I can easily substitute it, but I just want to do that later. So again, I still just want to find my change, my work done, just my work done. And we know to say, if the motor is lifting the water without accelerating it, then the work done will just be equals to the change in kinetic energy. Not kinetic energy. Will just be equals to the change in potential energy. And the change in potential energy, it's PE final minus PE initial. PE final, we saw to say it reduced to just 3 mg. PE initial, we saw it was 0 because the height there was 0. So that in the end, the work done will be equivalent to 3 mg. Here, m is the mass of the water, g is the acceleration due to gravity. We have no idea what the mass is. We know g is 9.8, but it's the mass where we have a problem. But all in all, this comes out as the expression for the work done. So let's take this back to the definition for power. Remember, we're looking for the minimum power. Power is work done over time. But we've just seen that the work done is 3 mg. So we still have that time here. So let's check again. The height there was 3, was it? Yes, the height was 3 meters. Okay, now this is where we are. Power is equals to 3 mg over t. But here we have a problem. The question only gave us 2 things. The height through which the water was being lifted, 3 meters, and the rate. And this rate was specified as 0.6 kgs per minute. The question did not say anything directly about the mass. It did not say anything about the time. We know g, so we can easily say this is 3 times 9.8, the g there. But the problem is with the m and also with the t. Now the question is, how do we sort out these two? How do you do that? Anyone? How would you sort out those? Because you know, if you multiplied 3 and 9.8, you'd get 29.4. But the problem hasn't gone. Mass over time. So we still have this challenge. Well, it turns out that they actually did give us what those two are. But they didn't just spell it out to us. Look at this quantity, the rate. They say the rate is 0.6 kgs per minute. What does this give you? What do you think this actually gives you? To understand what this gives you, you have to look at the units. This is a unit for what?
Mass.
And in the denominator, this is a unit for what?
Time.
The same 2 things that you are actually looking for. In other words, this rate of theirs, they didn't say what rate it was, but if you look at it, it's actually 0.6 kgs, and what you have in the denominator, it's 1 minute. What is this saying? It's saying that this motor lifts a mass of 0.6 kgs every 1 minute. This is what that statement is telling you. It lifts 0.6 kgs per minute. So it's lifting 0.6 kgs every 1 minute. So they didn't spell out exactly what the mass is or what the time is, but by observing what the rate is, we have managed to get what the mass is and also what the time is. We do not necessarily need to extract them one at a time, as in what the mass and what the time is. Instead, we can still just come here and factor in where we have mass over time here, we can put that rate. It will exactly still play out. But we can still do it like this. We've seen using our rate, mass is equals to 0.6 kgs. But if this is the case, then the time has to be 1 minute. But we need seconds because we know the watt is the joule per second. So we convert this 1 minute to seconds and we get 60 seconds. So if we now go back to our definition for power, we had this, but we now know what time is, and we also know what mass is. So our power is now equal to, where we have mass, we'll put 0.6 kgs. Where we have time, we'll put 60 seconds. So this becomes the expression that gives us the power. So now we just do the math. It's the 29.4 by 0.6. And we get 17.64. Then we divide this by 60. And we get 0.294 watts. And if you checked, this is the answer we expected. Where is it? Here. 0.294 watts. Any questions on this? Any questions there? Consider a question like this one, where, in this case, they're talking about something that happens in a cardiac test, cardiac function test. So don't get confused by the terms they're using here. All we want is the physics behind this. And what are they describing here? So the first part, let me say, starting from here, all this doesn't tell you anything about the question. Perhaps they start describing the question right there, walks. And what are they saying? They're saying here, this patient walks on an inclined plane or an inclined treadmill. But all I want you to get from here is this is an inclined plane. What does that mean? It means that this is a surface that looks like this. That is like this. But of course, you not to say a treadmill will just maybe have just one part, perhaps something like this, but it keeps maybe spinning like that, as in keeps rotating in such a manner. But of course, it doesn't spin in that manner. It spins backwards as you walk. So the person will be walking. So pardon my drawing skills. The person will be walking maybe something like this. So the person will be walking like this, too much a step. The person is trying to walk like this, and then this keeps spinning backwards, so that the person is more like just walking on the same position. So this is basically what is happening here. But all in all, this is not a flat surface like this. It's a surface where the top part is elevated to go up, such that you have an inclined plane. We don't really want to look at it as some weird thing. All we want to see it as is just an inclined plane. So I've reduced it to just a line like this one. Now, what is happening here? They're saying that estimate the power required for a 75 kg patient when the treadmill is sloping at an angle of 12 degrees and the velocity is 3.1 kilometers. So what are they saying? The sloping, the slope created by the treadmill or by this inclined plane is 12 degrees. That's one thing. Apart from that, what else are they saying? They're saying that the speed is set to 3.1 kilometers per hour. What does the speed there represent? The speed at which the treadmill is going to be spinning backwards. You know, if you have to practice on such an equipment, the idea is if this is you here at this position, the idea there is that you should maintain your position. You should remain in this position throughout. So as the treadmill rotates backwards, you run forward, but you don't run forward such that you start advancing on this equipment. You run forward just enough so that you maintain your position on the equipment. So in other words, when they say the speed on the treadmill is set to be 3.1 kilometers per hour, they are actually telling us that your speed must also be, since you are going to maintain this position, your speed must also be 3.1 kilometers per hour, but just forward so that you maintain your position. You have to match the speed of the treadmill so that you remain on the same position. For those who've been to the gym before and who've used this equipment, I hope you're able to understand exactly what I am describing here. So all I want us to get from here is whatever that speed they are giving us there, that is the speed of this object. And this is the speed the object has up the inclined plane. 3.1 kilometers per hour. Now, what is happening here? Estimate the power required for a 75 kg patient. So we're given the mass, 75 kgs. On a treadmill which is sloping at that angle, and the velocity is given by this. Now, how do we work out something like this? You see, the logic of the treadmill is that you are exercising against your own weight. You are exercising against your own weight. What do I mean? Well, you know to say for an object on the inclined plane, the weight of such an object will be broken down into two pieces, back to forces. The weight acts vertically downwards. The weight acts vertically downwards, but you sort to say this weight can be broken such that you have one force that acts downwards along the inclined plane, and the other force will be acting perpendicular to the surface of the inclined plane. But the one we are interested in is this one, the one that acts downwards. We've looked at this one before. How do you get this component of the weight that acts downwards? How do you get it? What is the expression we use for it?
mg sin theta.
Nice. So at this point, you guys, you really don't have to be stressing with this. It's something that you know to say it will always be mg sin theta. And the theta will always be the same as this angle here. If this angle is 12 degrees, you know to say even this one has to be 12 degrees. So it will be mg sin 12 degrees. So this is the weight. Now, if you're going to be running on an inclined plane at a constant velocity, and this velocity is specified to be this 3.1 kilometers per hour, what does this mean? It means that you must also exert the same force as the weight. If you were to exert a force greater, then you'd obviously end up accelerating, as in moving further, moving faster, moving forward on the inclined plane. But in this case, since you're maintaining the position, it means that whatever the force you are generating, it has to match your weight so that you maintain the same position. What am I saying? What I'm saying is here, if I was to remove the velocity just for an instant, the force that you exert on this, that is going to be pushing you forward. If you are not supposed to slide forward or to move forward or slide backwards, that force F must actually be equal to mg sin 35, sin 12, I mean. How is it like that? If I was to sum the forces along the direction of the inclined plane, I'm calling that direction to be x, this must be equals to 0 It's equals to ma, but because there's no acceleration again, constant velocity, it means that the acceleration is 0, so that this is going to be 0 here. With that in mind, there are only two forces in our x-axis. The force is F minus the piece of the weight going downwards, mg sine 12. This has to be equals to 0. So that your force, the one making you to go forward, has to be equal to mg sine 12. And this is the force that is actually doing the work. Now, how do we finish this? When you are running on this treadmill, you then notice that the power will be equals to the work done divided by the time. But how does it go here? You know, work done can be calculated by the change in potential energy. You are running at a constant speed, meaning there is no change in kinetic energy. So work done will only be seen as the change in potential energy divided by time. You remember how this ended up last time? When we are dealing with the change in potential energy, if your starting point is the reference point, 0, then your final position will be the final point. This can be seen as just mgh over t, because that is going to be your change in potential energy. You can look at it like this, or we can use that force. This is one way, but if you actually approach it from this point, you will have to know what the height is, your final height. But the other way that you can actually work out this is by getting work done as just force times displacement divided by time. This would be the quickest way to get the answer. How is this going to work? Well, we've seen the force that does work. The force, we saw it just came out as mg sine 12. But the question is, what will be the distance? And what will be the time? Because the mass is given. The mass is a 75 kg patient. G is 9.8. This is sine 12. But the question is, what are you going to use here as your distance? And what are you going to use here as your time? Which brings us back to what we described earlier on. They gave us the speed at which the patient has to be running. And the speed was given as 3.1 kilometers per hour. So how do we use that speed? The speed is given as 3.1 kilometers per hour. From this speed, we see to say that if the distance is 3.1 kilometers, then the time will be equals to 1 hour. You know, to say speed is distance over time. So I just said, like the same way we use that rate, I have said if the distance is that 3.1, then our time has to be 1 hour. We can then express this distance in meters, 3100 meters, and we can express this time in seconds. 1 hour contains 3,600 seconds. When we reach this part, then we are literally done. Now just taking these and taking them back to this expression that we had earlier. But where there is distance and where there's time, we'll now substitute the correct expression. Power now becomes equal to, where there is distance, I'll put the distance in meters, 3,100 meters, and where there's time, I'll put my time in seconds, 3,600 seconds. So this is what is going to give us our answer. Can you guys try to evaluate this? What are you going to get there? So you say you 135? 131. 131.5? 59. Okay. So can you guys just go through this? Okay, so this is in watts. We can write it to just 3 sig. If it is in 3 sig, we have 132 watts. So that becomes our final answer for this question. Any questions at this point? Okay, looks like this is everything we'll have. So we're going to end here. Tomorrow night, send me as many questions as you guys can. Share them in the same Syllabo app. Invite your friends. Let's learn together. And would like to speak. Yes, Sarah, how can I help you? Hi, Sarah, you have your hand up. Sarah, you have your hand up. You can ask. Okay, so we can end here. Sarah, if you still have your question, you can reach out to me directly. I'll be glad to help you out. Yeah, so you guys can invite your friends. Let's learn together. We'll see you guys tomorrow evening.